Now, so how do we calculate the capacities? Okay. So, let us look at for an uncracked section, how to estimate this diagonal cracking load. Okay. So, as we said, when you test a beam like this in a shear dominant region, you can have principal tension form like this, and then the crack will basically follow the direction of your principal compression, as we have explained in the previous slides. And this is what you are going to have. And if you take an element in the neutral axis, you will have both shear and axial stress. When you convert it into principal tension and principal compression, you will find that this angle theta will be less than 45 degree, and that is basically your crack angle, right. We have seen that. Now, how to calculate the capacities for this, okay? And we know that the failure is going to be governed when sigma 2 becomes Ft, which is a tensile strength of concrete. Okay. So, when sigma 2, the principal tension, becomes tensile strength of concrete, it is going to fail. Now, from our Mohr circle, from your equations, we know what are the equation for your principal tensile strength or tensile stress, which is tau xy plus fx plus fxy by 2 the whole square, right. So, there is no fy. So, fx is nothing but your FCP, which is the average pre-stress. So, if you substitute, this is the equation for your principal tensile stress, right. Now, what all these denominated? Tau is the nominal shear stress due to live and dead load, and FCP is the compressive stress at the centroid due to pre-stressing, and Ft is the direct tensile strength of the concrete. So, now we need to find out at what levels of tau this Ft will become equal to the tensile strength of the concrete. Tensile strength of the concrete is typically, assumed as some function of, or I should say some constant times square root of FCK. Okay. Different codes give you different values, but typically it is measured as a fraction of your compressive strength. Now, let us look at it. So, this, if you do the simplification, and if you do, the tau can be expressed in terms of principal tensile strength like this, Ft into square root of, you do some simplifications of this equation that we have done, and if you do that, tau can be expressed in terms of principal tensile strength and the amount of pre-stress in this form. Okay. Now, if I take tau is equal to tau Cr, because we are interested in calculating at what shear force it will lead to that diagonal shear crack, and Ft, if I am taking it equal to FCR in a very simple way, modulus of rupture, let us take that, and you know that FCR we take it to be 0.7 square root of FCK. Different codes give you different value, you can be 0.2 also, So, let us say now. And now, from crack angle also now I can find out, because we are doing all these things for an uncracked section at the incipient at which it is going to crack, that is what we are trying to calculate. So, from Mohr circle again, the crack angle is tau 2 tau Cr divided by FCP, which is your average normal pre-stress that what you have put. So, if you plot these variations, if I can plot the variations of your tau Cr to FCR in the y-axis, similarly the amount of pre-stress to modulus of rupture FCR, there are two things that I am plotting. So, what is that we are plotting here? So, in the secondary axis I am also plotting the crack angle. Now, first let us look at only the tau Cr by FCR ratio to FCP by FCR ratio, right. So, if FCP becomes higher, that means I am applying lot of pre-stress compared to that of the tensile strength of the concrete, right. So, as you can see, if I put lot of pre-stress FCP by FCR equal to 5, and you find that the shear at which it is going to crack again becomes close to that of 2.5. If I put only 1, then you find that the tau Cr is less. So, what we can say, higher the amount of pre-stress in terms of its tensile strength of the concrete, that means if I put more pre-stress, I am getting higher diagonal cracking capacity, right. That is one thing. So, that is somewhat you can see that it is linear. If I put negative means basically pre-stressing is not pre-stressing is in compression, but it is in tension. So, you know that it is going to fail like this, right. So, that means it is going to fail in basically in normal stress in tension only, right. So, that is not going to be good. So, always we are looking at it from this value, okay. So, when the pre-stress is in compression. Now, what happens to theta CR? So, you see here theta CR again when your FCP is -1, that means I am applying a tension, right. You find that it is going to be cracking at 90 degree, that means I am going to have a vertical crack, right. If my FCP is very high, then what happened? That is what we said, theta CR is going to become shallower, and again the crack always we are trying to measure with respect to let us say this, if I this with respect to horizontal is what we are measuring theta CR, right. So, that is the reason. So, if this is theta CR means this is 90 degree when your FCP is -1 times FCR, that means pre-stressing is in tension, right. But however, if you look at this theta CR, if I put lot of pre-stress at this point, the crack angle becomes as shallow as 20 degree, right. So, higher the amount of pre-stress, shallower is the crack angle. Higher the amount of pre-stress, higher will be the diagonal shear cracking capacity. So, that is what we are trying to find out. Now, let us see. So, that is what we said, okay. So, now let us see, we can find out an expression for this VCR. Now, the same expression only. Now, again we are trying to simplify it, right. So, if you do that, tau CR can be simplified in this form of FCR square plus square root of FCR into FCP, and we know the shear is VQ by IB. So, I want to express this VCR equation. So, VCR can be expressed in terms of tau CR, in terms of tau CR into IB by Q, right. Now, you know that tau CR is also basically this. So, basically VCR is basically what we are saying is tau CR into IB by Q. Now, you see what is tau CR? Tau CR as per this formulation is square root of FCR square plus FCR into FCP into IB by Q, right. So, in this way I can find out an expression. Now, if I know the cross section that I am dealing with, FCR is a material property, and FCP is the amount of pre-stress. So, it is given to you, right, and I, B, Q are section properties. So, all of them are given to you. So, from here I can calculate what is the diagonal shear cracking capacity. So, that is what we are going to do. So, if I am taking only the rib of T, L and I beam which are effective in shear, then we can what we can do? We can find out an expression for your VCR in a very simple way. That is what we are going to look at it. So, Q is equal to A into Y bar, we know that it is the first moment of area. If I am calculating, let us say at the CG point, and this is the area that I take the moment of that area about the neutral axis. And so, in that way Q is going to be BD by 2 into D by 4. So, Q becomes PD square by 8 and I by Q becomes 0.67 D for a typical rectangular section. So, VC naught works out to be, this is your diagonal shear cracking capacity, 0.67 BD into square root of FC square FCR square plus. Now, 0.8 is nothing but some reduction factor, code wants to estimate in a conservative way. So, they do not take the FC, they do not want to take the full 100%. So, they want to reduce the beneficial effect of pre-stressing. So, that is the reason this 0.8 factor comes. Now, VP, this is the vertical component of pre-stress. Now, either you can take VP and subtract it from demand, or you can add it to the capacity. You cannot do the both. Okay. So, the beneficial effect of pre-stress Either you reduce the demand or increase the capacity. So, either way, one of them we have to do, right. So, now this is for diagonal shear capacity or web shear capacity. So, we found an expression for your web shear capacity in the previous slide. How about expression for flexure shear cracking? Okay. Now, what is the meaning of flexure shear cracking? As we have said, a flexural crack will form like this, then it converts itself into a shear crack, right. So, that is what we are trying to form. So, a diagonal crack will be formed after an existing flexural cracks converts itself into a shear crack, right. So, let us look at it. We are looking at two cross sections, which is B and C. They are separated by a distance d by 2. Let us say I am taking a section or the locations where there is no, I should say, it is subjected to constant shear. So, this is a constant shear. Okay. So, if you see this, this is a kind of loading that we are considering, and your shear force, you know that it is going to be constant, which is V is equal to P, right. So, this is plus minus. So, that is what we are looking at. So, we are looking at it somewhere in this region, okay, where the shear is constant. Now, you see that this is let us say at section B, I am taking the shear force diagram and bending moment diagram. Let us say that at this section, let us say at B, it has moment has reached the value of cracking moment. So, I am going to develop a crack like this. Now, what would be the shear that will be applied? Which will be same, which is equal to VCR, or which is equal to the shear in general, because shear remains constant here, right, in this region. So, at C is also the shear demand is going to be still equal to V. So, that means VCR is equal to V at this particular point. Now, let us look at what is the change in the moment between B and C. So, originally this is at B, now at C MCR has become M, right. So, you see that now we know the change in the moment, we know that V is equal to dm by dx, right. So, the change in the moment divided by the distance between them, which is distance between them is basically d by 2. So, this divided by the distance is nothing but your average that I am taking. So, basically here the shear is constant. So, V can be equated to VCR. So, you can find that VCR, if I take that as a shear demand as V, then it is going to become 2V, then 2 will get cancelled. So, it will become V into d by 2. So, again we can write that M by V is, if I divide everything by V, then this will become M by V divided by M by V is equal to d by 2. That is what we have drawn here, right. So, I am doing some simplifications to explain how to calculate your flexure shear capacity in shear, right. So, if you substitute that, I think this is what we have, and then we can write V in terms of this formulation with some simplification. So, you can see that now what we have done here is we have brought d by 2 on this side, taken MCR by V on this side, and then I am finding out what is the expression for V in terms of other variables, right. So, that is what we have done. Now, this one you see here, this is the shear at this location at C, okay. This is this expression V, which is nothing but MCR divided by M by V at that particular section. So, this is at C, right, minus d by 2. So, this is the shear at C due to live load and superimposed dead load when the moment at section at B is MCR. So, at this means at section B it has reached the cracking moment capacity. Now, at section C we are trying to find out what is the net shear that is acting, okay. So, now why are we doing this is I will tell you. We want to find an expression for your flexure shear capacity in shear, right. So, you see here the shear at that section C is this plus whatever the beneficial effects of your vertical component of your pleistocene. So, from experimental work we know that an additional shear, so that means basically what? The section has already cracked in flexure. So, what is that additional shear that I need to apply to convert that flexural crack into shear crack, right. So, that is always, as I said, it is expressed as a function of your compressive strength. So, that is 0.05 into BWD into square root of F prime C. So, this different codes gives you different value, but you can take this value as a thing. So, it is required for flexural crack form for the inclined cracks to propagate. So, if you substitute that VCI as this, right. So, basically this is the additional shear required to convert flexural crack to shear crack, and this is the shear at flexural crack. Already the section is cracked in flexure, there is a shear that is acting in the section. So, so this plus this is your flexural shear capacity, and this is always the vertical component. So, this is vertical component, that is going to be there, right. So, we can say that in the flexure shear cracking zone, the tendon slope will be small typically, and now typically you see here that, and the d by 2 in this case it can be removed for simplicity, so that we can find a conservative estimation for the shear, right. So, if you see that, that is how we end up with this expression for this. This is shear for flexure shear. That means shear capacity of a section that is already cracked in flexure, and how much additional shear it will take to convert it into a shear failure. So, this is for the shear capacity of a section that is already cracked in flexure. So, let us put it that way, VCI. Okay. So, with this simplifications we can find out. So, for any sections, if you know the ratio of shear to bending moment distribution, then I can get my MCR, and this is an additional shear that will be required to convert itself from flexural crack to shear crack. So, basically there are two failure modes. One is section will fail in diagonal shear tension in a web shear crack mode, that is we derived one expression VC naught. Then the second one is the section that is already cracked in flexure, then it converts itself into a flexure shear crack. So, that is what we have derived two expressions. Now, let us look at the IS code provisions and how they take care of that. Now, you see here the VCR equation in IS code, just similar to what we have derived, that is also same, m naught into V by m. Here the code tells you m naught, previously we derived MCR. So, that is the only difference, and this is some form of your shear strength, concrete shear strength equation. Now, what is the equation here? Fp is the effective pre-stress in the tendon after, they are all same, this equation and the previous equation, they are all one and in the same form, only the coefficients are different. Now, what is FPK? FPK is the characteristic strength of pre-stressing steel, and psi C is the ultimate shear capacity of the concrete, that we take it from table 8 of IS 1343. Now, what is psi C? And some form of a concrete shear capacity equation, and that is given in this 0.85 into square root of 0.8 FCK into square root of some empirical formulation, and beta is you take depending upon the concrete strength and your tension reinforcement ratio, you take the beta value. So, typically whichever is higher that you take in this equation. So, this is your tau C. Now, what is D? D is the distance from the extreme compression fiber to the centroid of the tendon, and m naught is the moment initiating a flexural crack, or and m and v are the moment and shear due to ultimate loads at the design cross section. At any cross section, even before design, we know what would be the moment and shear acting in the cross section, that will be given to you. So, you can find out that ratio, right. So, now let us see how do we the other equation. So, you see here m naught into m, you see m naught by m into Vu is basically the shear corresponding to the moment m naught. That means, this is a shear that is acting when the flexure, when the pre-stressing moment is corresponding to a moment of m naught. That means, which is going to decompress or nullify the effect of pre-stress. You see, pre-stressing we put some horizontal stress, when the moment is getting increased, that horizontal the normal compressive stress will become 0. how much moment I need to apply to nullify that pre-stress is what we call that as m naught, right. So, that means m naught by mu into Vu is nothing but what would be the shear acting when the flexural crack is forming. So, that is what it is, right. So, that again code is giving you in a simplified. So, we know how to calculate that. This is the stress, pre-stress that is there, and code is assuming it in a conservative way. So, that is why this 0.8 factor is coming, okay. That is why that 0.8 factor is coming. So, this 0.8 is coming from there. Otherwise, I am reducing this. So, see, always the capacities we want to estimate it in a conservative way. So, there is some, you can say this kind of a reduction factor, right. Now, let us see what is the maximum permissible shear stress. Now, I told you from Mohr circle from the previous discussions, we should always make sure that the section is not going to fail in principal diagonal shear compression, right. When concrete fails in compression, it is going to be a brittle mode of failure. At any cost, we need to prevent concrete from failing in shear compression mode. So, how does the code allow, make sure that the designer is not going to design the section to fail in shear compression? We should always make sure that the nominal shear should be less than tau C max. So, tau V, that what we calculate, should always be less than tau C max. Now, what is tau V? Tau V is what we are given here is V divided by B into dt, where dt is the greater of dP or d, and dP is the depth of the extreme compression, the pre-stressing steel from the compression fiber, and typically minimum of 0.8 is considered. In shear, when we take it, typically the centroid of the pre-stressing steel may be close to the neutral axis, then you cannot take that lower value. You should at least take 0.8 H, and D is the depth of the centroid of the regular or non-pre-stressed steel. Okay.